Hello everyone. I would like to take a look at two examples where we'll be using our double angle identities. In one example, we're just going to be finding the exact value for some double angles, and then the second example, I'm going to use a double angle identity to help me solve an equation. So anyway, the first example says if the cosine of theta is 3/5 on the interval from 0 to pi over 2, I want to find the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So we got three different double angles we want to find. The way that we're going to find these is by using our different identities. And to use those identities, I do need to know the values of the sine of theta, the cosine of theta, which they give me here, and then I do need to know the tangent of theta as well. So we're going to use our given information. We're going to use the cosine of theta to help me figure out what the value for sine of theta is and what the value of tangent of theta is. The other piece of information they're giving me here, this interval from 0 to pi over 2, this is basically just telling me what quadrant theta is in. So what quadrant the terminal side is in. So from 0 to pi over 2, that just tells me this is in quadrant 1. So if I just do a little sketch, so because that interval, I know I can just focus on the first quadrant. Cosine is the adjacent side over the hypotenuse. You could think of this as it's the x value over the radius. So we're looking at an angle sort of like this. So this would be theta, this angle. This change in x, that's 3, or the adjacent side, and then the hypotenuse is 5. All right, we could use the Pythagorean theorem to find out our missing side, but this is a Pythagorean triple, so this is a 3, 4, 5 triangle. Okay, so now that I have all those sides, I can figure out our other two trig ratios. So the sine of theta, this is equal to the y value divided by the hypotenuse, so this is 4 over 5. And then the tangent of theta, this is y over x, so this is 4/3. And then our other one we had, which was given to us, I'm just going to jot that down here as well, the cosine of theta, 3/5. And now that we have these three different values for our trig ratios, we can use our double angle identities to help us find the exact value for these three. So the sine of 2 theta, the identity for this is 2 times the sine of theta times the cosine of theta. So we'll start with this one. So this is what we're trying to figure out, and we're going to use the identity because we know the sine of theta and we know the value for the cosine of theta. So we have 2 times the sine of theta is 4 over 5, and then the cosine of theta is 3 over 5. And now we just have to multiply these together. So then that's going to give us the sine of 2 theta. So 4 and 3 is 12 times 2. It's going to be 24 in the numerator. And then the denominator, 5 times 5. So the sine of 2 theta is 24/25. Okay, so there's the first one. Let's do the cosine of 2 theta next. Now with the cosine of 2 theta, we actually have lots of options. There's 3 different identities that are frequently used for the cosine of 2 theta. We can pick out any of those that we would like. The reason that we have 3 and the reason that it works out that way is because of the Pythagorean identity, that relationship between sine squared and cosine squared. They're all going to give you the same answer, So whichever one you prefer, that's the one we can use. I'm just going to use cosine squared of theta minus sine squared of theta. And again, we know the value for cosine theta sine of theta, so we can plug that in. So cosine of theta was 3/5. Then we need to square that. And then minus sine squared, so 4/5. And we'll square that one as well. Squaring a fraction, square the numerator, square the denominator. So this is 9 over 25. And then minus 4 squared is 16 over 25. And then subtracting these two fractions, we do have a common denominator. So then 9 minus 16, that looks like negative 7 over 25. Okay, so the cosine of 2 theta, we do end up with a negative value. But if we think about that, that does make sense. So the cosine of 1 theta, so just a single theta, gave us a positive cosine. So we had positive 3 over 5. If I double this angle, so if I, whatever measure this is, if I take that and I double it, I do actually end up over here in the negative x-axis. So now my change in x is negative, while my hypotenuse is still positive. So that gives us that negative value for the cosine of 2 theta. All right, and then our last one, let's do the tangent of 2 theta. So the identity for this, 2 times the tangent, and that's going to be divided by 1 minus the tangent squared. And again, we know the value for tangent theta, so we just have to do some substitution. So 2 times 4/3, then 1 minus 4/3 squared. All right, in the numerator, that's going to simplify to 8/3. In the denominator, 1 minus, square the top, square the bottom, 16 over 9. All right, just working with this a little bit more. 8/3, 1 minus 16 over 9, so 1 is the same as 9 over 9. And then if we do, let's see, 9 minus 16, it's negative 7/9. And then we can change this to multiplying by the reciprocal. And then to finish up, so we can take out a common factor of 3 from the 9 and the 3. So that leaves me with 3 up here, and this will simplify to 1. So we end up with negative 24 over 7. And there we go. If we take a look at the value for the tangent 2 theta here, negative 24 over 7, we can see that we also could get that from dividing our values for sine of 2 theta and cosine of 2 theta. So if I take sine divided by cosine, 24 over 25, divide that by negative 7 over 25, we do get the same value. All right, now a little bit of a different example. Let's do one where we're going to use one of our double angle identities to help us solve an equation. So we talked a little bit about solving equations already, but remember, we want to get it down to a point where it is a single trig ratio set equal to some value. And then after we have that, we can use our unit circle, or kind of this idea of inverses, to help us find out how big that angle is. So our equation, the cosine of 2 theta is equal to the negative sine squared of theta. So they don't match, they're not the same trig ratio, and we can't factor this, so that's when we have to rely on one of our identities. So I'm going to take this cosine of 2 theta, and I want to substitute that out. Now, as I talked about, cosine of 2 theta, we actually have 3 different options that we can use. And there is one of those options that makes the most sense in this case. Because my right-hand side is the sine squared of theta, I want to be able to replace the cosine of 2 theta with something that only has sines in it. So that is 1 minus 2 times sine squared. So using our identity, the cosine of 2 theta is the same as 1 minus 2 times the sine squared of theta. So just substituting that out. And then our right-hand side is going to stay the same. Again, I'm picking that one out because this identity only has sines in it, and the other side of my equal sign had sines in it as well. Okay, so now we have sine squareds, so we can combine some like terms. So I'm going to add 2 sine squared to both sides. That leaves me with 1 is equal to the sine squared of theta. I want this to be just sine to the first, so let's take the square root of both sides. And we end up with the sine of theta is equal to, and then we're taking the square root, so plus or minus 1. Okay, so now our 2 options, we have the sine of theta, when is sine equal to 1, and then also when is sine equal to negative 1. So now using our inverses, or taking a look at the unit circle, figure out when is that y value equal to 1 or negative 1. So our options here, so sine is equal to 1 when theta is pi over 2, and sine is equal to negative 1 when our angle is 3 pi over 2. And there's our 2 answers. Let me just combine those together. So using our double angle identity, or one of them, we're able to work with our equation, get it to a point where it's all sines, and then we can finish solving like normal.